Okay, so yesterday we learned about naming. We reviewed, really, you've learned that, I'm sure, in grade 10. For binary ionic compounds, meaning that they're made up of only two elements, a metal ion and a non-metal ion. The metal ion keeps its name, sodium, for example, and the non-metal ion gets its "ide" name, chloride, for example, sodium chloride. What we want to talk about now is something called polyatomic ions and how we can name and come up with formulas for those. So again, I'm not sure where everyone is at. Has everybody got the title down if we're ready to go? All right. So what is a polyatomic ion? Well, a polyatomic ion is a group of nonmetal atoms that have a charge. They can ionically bond to other ions. Most of our polyatomic ions end in "ate" or "ite", all right? And there are a couple of exceptions. We've got an OH with a negative charge, and I like to put the charges on the outside of the bracket, so it's not a big deal, but I'm going to get rid of it there. OH minus and CN minus, all right? And for this course, the only polyatomic ions that we're going to use are found on the data table on the periodic table, right? The back page that we associated with that. So if you're done writing, you can have a look at your chart on your table, and you'll notice they all end in "ate" or "ite", and then there's the two that are hydroxide and cyanide. There is also another one there, and that is the ammonium ion, but it's distinctly different than all the rest of the ions. How is the ammonium ion, if you're looking at your table, different than the rest of the ions that are in that chart? Yep, Jess? It has a positive charge. So it behaves as if it is a metal. Remember, our metals are the ones that have positive charges. So ammonium, which has a formula of NH4, behaves as if it's in group 1, all right? The rest of them are negative ions. You'll notice they're made up of all nonmetals, and they behave as if they are nonmetals, some of them with a -1 charge, some of them with a -2, all right? Now, in the grade 11 university, I make them memorize all these and a lot more. We go over in the procedure on how to figure out to create many ions. There are many more polyatomic ions than exist on this chart. But I'm not going to have you do that in this course, so the only polyatomic ions you have to worry about are the ones on this chart, okay? All right. Let's jump ahead to the next slide, which I believe is the chart itself. That's simply a scan or a picture of the chart. And you can see there we've got something called acetate. Now, acetate can be written in two different ways. I don't care which way you write it. You'll notice the first way has the C's spread out and the O spread out. And an acetate is a special type of ion. It's what we call an organic molecule. We'll learn more about organic chemistry later on in the course. And when we write out an organic molecule spread out like that, CH3COOH, it gives us a little indication as chemists on how to draw that particular molecule. So I've been acquainted with that molecule for a long time. I see CH3COOH, and I can imagine exactly the way that molecule looks. And you guys can't yet, but you might by the end of the course. But that's why it's written slightly differently. This particular form simply has all of the atoms kind of put into a pile like we normally write something like that. Okay, hypochlorite, chlorite, chlorate, perchlorate. You'll notice that these are all kind of related to each other. That's what I teach them in the 3U. Maybe you could tell me what's different between a hypochlorite, chlorite, chlorate, and perchlorate. What is changing each time we're looking at those particular ions? Isaac? Yeah, the amount of oxygen that's in it, right? The perchlorate is highly oxygenated. There's many oxygen atoms in there. The hypochlorite has few. That's how we name them, and that's how we know that they're different. Okay. Hydrogen carbonate or bicarbonate, chromate, dichromate, manganate, and permanganate. And you'll notice this is a little different. Chlorate and perchlorate have the same charge but different number of O's, but manganate and permanganate have the same number of O's but different charge. So it's a slightly different way of representing it. But it doesn't matter. All you need to know is, if we see a polyatomic ion, you can go to this chart to find its name, and if I give you that name, you go to this chart to write down the ion. Okay? Any questions or concerns? All right, let me just talk a little bit about what a polyatomic ion is for a moment before we get into the naming. We've already done Lewis diagrams, and we did a Lewis diagram for sodium chloride. So we had sodium, right? And we had chlorine, and we did this type of thing where we transferred the electron, and we end up with a sodium ion, positive charge, no dots, and then a chloride ion, 8 dots, right? And that's the Lewis structure for sodium chloride, all right? Instead of having sodium, I could actually put an NH4 in its place because it is also +1. So I could actually have a compound that is NH4 with a Cl. And this would be called ammonium chloride. All right? It's called ammonium chloride. Now, what does this look like compared to this? Now, we don't need to know this. You don't need to write this down, and none of you are, which is good. But let me show you what an ammonium looks like. An ammonium has 4 hydrogens bonded to it, all right? Much like water has 2 hydrogens bonded to it, okay? And we're going to learn how to draw these molecules. But the difference between a water molecule and an ammonium molecule is that an ammonium, yes, it's made up of N's instead of O's, and it's got 4 H's instead of 2 H's, but the ammonium molecule has a charge. It has an extra proton in its structure to give it a +1 charge. Or you can think of it as if it's missing an electron. It gives it a +1 charge. So this is the Lewis diagram of an ammonium ion, just like this is a Lewis diagram of a sodium ion. So if I put ammonium with a chloride, it just means that the ammonium ion is stuck to the chloride ion, and it makes ammonium chloride, all right? So each of these polyatomic ions actually have these molecular structures, which we're not going to worry about in this course, but they do, and they have a charge associated with them, which means they can stick to oppositely charged ions and form ionic compounds. All right, let's take a look at some names. So, you know what you're going to write here? Don't write down, don't make a grid, all right? Don't make a grid. Let me back up here. What's this here? Let's back up. Back up, back up, back up. Don't write down a grid. All I want you to write is e.g., example, right? E.g. If you already made the grid, that's great. And then just write down Li2CO3. And let me get this thing out of the way. Al brackets, NO2 brackets 3. And NH4, look at there. I didn't even know that one was coming up. I think we know the name of that one. And let's now come up with the names. Now, you're going to give me answers already? Just relax. Just take a break. Everybody take a break. Whew. Nice. Now, even though these compounds contain 3 different atoms, the name will always have 2 parts. Just like we name sodium chloride with 2 parts, the positive ion sodium and the negative ion chloride, the names of these will also have 2 parts. There will always be the positive part name, all right? And there will always be the negative part name. So the naming system is always something, something, all right? It will never be, the answer will never ever be lithium 2-carbon 3 oxide. You see what I'm saying? You don't just throw words together and say, hey, that must be the naming system. The proper name has a positive chunk name and a negative chunk name, all right? So I'm hoping you can see, and I'll get a different color, that if we break this down here, there's the positive piece and there's the negative piece. Well, let's now name those pieces. Now I am asking on you to tell me the name. Amy? Excellent. Lithium is a lithium ion. We already know the metal ions keep their name. This is obviously more complex than something like a nitride or an oxide. So we don't look on the table. We look at the back. We track down the CO3. I'm struggling. Where's the CO3? Where is it? Oh, yeah, right here. We see that it's carbonate. What did I just do? Why did I put it? What is charbonate? Carbonate. That was sad. The eraser doesn't work. When you pick up the eraser, it doesn't do anything. It still thinks it's a pen. Fails. So I scribble. Name of the next one. Just take a rest there, Hermione Granger, for crying out loud. Man. What do you got?
I got aluminum nitride.
Excellent. Aluminum nitrite. Now, the way you get nitrite is to look at the NO2. This 3, where did the 3 come from? Where does this 3 come from? Yep. It comes from the crossover of the aluminum. So we're always looking inside the brackets for what the thing is. When we do the formulas, that's where our numbers will come from when we cross over. Last name here. Shay, what do you got? Well, that end piece we've seen before, right? That's the negative chunk. What is that? What do we call that negative piece on the back end? It's chlorine. And what ending do we give it when it's on the back end? Well, I don't see a chlorine on this chart, so I'd have to go to my periodic table. There's the chlorine. But when we put the chlorine at the end of a compound, we don't say chlorine. What do we say? So we've got chloride on the end. Nice job, chloride. Now, I just said we never call it nitrogen 4-hydrogenidium or something like that. So now I can go to that chart, see if I recognize anything. Do you recognize anything? All right. Is it a visual issue? Do you can? All right, let's bring it closer. Maybe it's proximity.
I'm looking for NH.
You're going to look for NH something. It's got to look exactly like that. It's got to look just like it. It's the last one on the right.
I don't know how to pronounce that.
Well, do your best. Whoa.
I don't know.
That's okay. That was fun. Ammonium. 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 I was going to make fun, but I am recording this. This is going to go out online, so that would just be mean if I made fun of that. Excellent. Ammonium chloride. All right? So thank you very much. Oh, no, you can hang on to that. You can just use that. Oh, okay. All right. So be careful with the ones on the front. NH4 is going to be the only one. Ammonium. Excellent. Let's continue. That was fun. Now we're going back the other way. Example. That's all you write. Write down the names, and then we're going to be crossing them over again. If you've already completed this, there's a sheet on Google Classroom that you can start to do.
I'm working on that right now.
Good. No need to. If you see how this is done and you've gone ahead, awesome. Okay. This is very much like we did with the simpler compounds. Write down the positive chunk with its charge. We'll need our periodic table. Now the negative chunk will be larger. It'll have its formula with brackets, but its charge will go on the outside of the brackets. We just cross it over like before. Ammonium is the exception to that. So you'll never forget that, right? That's called teaching by humiliation. No. No, it's just a summary of the both together. So they're both practice sheets. So you can just work on the practice sheets. Let me guide you through this one. Is anybody with me? I feel like I'm teaching in 5 different positions here. One person's doing the worksheet. Is anybody following me here? We're following, most of us? Okay, that's good. Makes me feel like I'm actually doing something. All right, so aluminum. That's just an atom. We've dealt with that one already. Going to my periodic table, Al. What's the charge on an aluminum ion? Yep, +3, right? It's losing +3. We're going to just keep that in mind. I'm not going to write it down. Or, yeah, maybe we'll do it on the first one. I'll write it down to see the crossover. +3. But again, we're probably better than this. We don't need necessarily have to write that down. Chlorate. I go to my table. Could somebody tell me what the chlorate ion is? Just got to find it on the chart and tell me what it is. Jess? ClO3. Is that what you said? Put brackets around it. What's the charge on that? -1. It might just put, oh, it does have a 1 on it. Excellent. -1. -1. Again, you do not have to necessarily write that down. Crossing it over. We'll use a different color because I have access to it. Puts it over there and puts that over there. We don't write the 1, but we do write the 3. I'm going to rewrite AlCO3 brackets, sorry, ClO3 brackets 3. I dropped an L. I put it back. Al brackets ClO3 brackets 3. Okay? Remember, this 3 tells me that I have 3 of those chlorates. So my picture for that would be pretty big and complicated. It would have an Al maybe in the middle with 3 big chlorates around it. I'm not going to make you draw that, but that's what it would look like. Okay? Just as a reminder, how many oxygen atoms would be in this thing? How many oxygen atoms would there be? There'd be 9. 3 times 3. Because there's 3 chlorates, and each chlorate has 3 oxygen atoms. 3 times 3. That's just a reminder of the way the formulas work. Magnesium sulfite. If you see how to do this, go ahead of me with pencil. Don't wait for me. Magnesium, sulfite, find the sulfite, brackets, cross over the charges, put it down, right? Don't feel you have to wait. I'm going to just proceed with some slowness so that you can get ahead of me. Sulfite is right there. SO3. What's the charge on a magnesium? 2. What's the charge on the sulfite? 2. So when we cross over the 2's, what do we do in the end with those 2 2's? You cancel them out. That's it. Magnesium sulfite. Yep. No, it doesn't. But I always encourage you to put brackets in case there's a crossover. If you come across that in a textbook or as a question, it won't have the brackets, which makes it tricky to find where the positive chunk and the negative chunk is. But it's not too bad. If you leave the brackets like that, I'd say, let's say it was on a test or something, I'd say, way to go. Good job. Okay? Ammonium. Ooh, ammonium. And, oops, NH4. Again, +1. I'm not going to write it down. Bicarbonate. HCO3. And what's the charge on my bicarbonate? What's the charge on the bicarbonate? -1. +1, -1, cross them over, leave it. Again, you've got the brackets there, that's fine. But you might see it without the brackets. And if you see it without the brackets, and I'm going to write it on the board, it'll look like this. NH4, HCO3. And you might ask yourselves, why didn't they put those H's together? Why wouldn't they just say NH5CO3? And that's to tell you that's where the positive chunk and the negative chunk will be, and then go looking for the names. Okay? Calcium hydroxide, Ca, hydroxide, OH. What do I need to finish this off? You tell me. Check your charges. Cross things over. Stephanie, what do you got? With the 2 on the outside of the brackets? Correct. Yep. You do not want the 2 on the inside of the brackets. That's a different thing. So there you can see it says question sheet, which means I've got a couple of other sheets for you to do. Let me just look ahead here. Oh, review game. We're not going to do that right now. We're going to let you work on the question sheets. So I'm going to stop my recording. And then we will deal with that in a minute. Save.